All right, this is section 3, Riemann sums and definite integrals. So we're going to start off with a region bounded by the graph of f of x equals the square root of x and the x-axis for 0 to 1. We talked about this limit yesterday, or last class. If c sub I is the right endpoint of a partition given by this width, and delta xi is the width of the ith interval. So basically, we're doing the same exact thing we did before, except that it takes us a whole bunch more work. But we can make these rectangles as wide as we want. Riemann sums are essentially just that. So we are finding the limit as n approaches infinity of the sum of I equals 1 to n of the square root of c sub I, which is I squared over n squared, because it tells us to use that, times delta x sub I, which is 2i minus 1 over n squared. Because we take c sub I minus I minus 1 squared over n squared. There we go. When we find this, we simplify it down. We are going to find the limit as n approaches infinity of 1 over n cubed times the sum from I equals 1 to n of 2i squared minus I. When all is said and done, that's how that'll simplify. And once we actually do that work, we find that the answer is 2/3. And we ask ourselves, was there a better way? Because this would take us a lot of work, which we will talk through in class too. But that is what we call a Riemann sum. We have an interval where my function is defined. Delta x sub I is the width of any given interval. C sub I is any point in that random interval. A Riemann sum is basically just adding up the rectangles. So a left Riemann sum is when C sub I is the left endpoint. Right Riemann sum is when C sub I is the right endpoint, and a midpoint Riemann sum is when C sub I is the midpoint. In the last section, we did left and right Riemann sums without calling them that. So a norm of a partition is the width of the largest subinterval of a partition, as denoted by these straight lines around our delta. A regular partition is when every subinterval is of equal width. So a regular partition, the norm is equal to delta x, which is b minus a over n. b minus a over the norm is always less than or equal to the number of partitions. There we go. Then that takes us to definite integrals. A definite integral is the limit of the Riemann sums. Basically, we add up all of the rectangles as n becomes bigger and bigger and bigger and bigger and bigger. So our norm is becoming smaller and smaller and smaller and smaller. It has to be called integrable if that limit exists. The limit is denoted by the limit as the norm approaches 0 of I to n of f of c sub I delta x sub I. Notice it looks a lot like our indefinite integrals, but this is a definite integral because it has a lower limit, which is a, and an upper limit, which is b. So a definite integral will give you a number. An indefinite integral will give you a family of functions. This theorem, continuity implies integrability. If f is continuous, then it must also be integrable, and the definite integral exists. So let's evaluate a definite integral. So we are using the definition. So we are finding the limit as n approaches infinity, or realize we could write the limit as the norm approaches 0. That's the same thing. Okay, those two things mean the exact same thing, just a different way of writing. From I equals 1 to n of f of c sub I delta x sub I. So delta x will be negative 2 minus 1, oops, delta x will be 1 minus negative 2 over n, which is 3 over n. C sub I is negative 2 plus 3i over n. So we are taking 2 times negative 2 plus 3i over n times 3 over n and finding that limit. So we take the limit as n approaches infinity of the sum from I equals 1 to n of negative 4 plus 6i over n times 3 over n. Oops, there we go. And that means we're taking the limit as n approaches infinity of the sum from I equals 1 to n of negative 12 over n plus 18i over n squared. So when we take this, we rewrite the sum. We have the limit as n approaches infinity of negative 12 over n times n plus 18 over n squared times n plus 1 over 2. Simplify a bit. We get negative 12 plus 9n plus 9 over n, which is negative 12 plus 9 over n. As n approaches infinity, this becomes just negative 12 plus 9. The area is negative 3. There's our definite integral. So, here's our theorem. The definition of the definite integral as an area of a region. The area is equal to the definite integral from the two sidelines. This is always between the graph and the x-axis, though. If we want to do something else, we have to write it a little differently. So we're going to find each of these areas using a geometric figure. So the area from 1 to 3, right, bounded here, of the function 4. 4 is just a horizontal line. So we're really just finding this area right here, which is a width times a height, which is 2 times 4. That area is 8. If I look at x plus 2 from 0 to 3, let's see here, 0 to 1, 2, 3. There's my bound. All right, if x is 0, that's 2, and then 3, 4, 5. Here's the area I'm looking for. That is a trapezoid. So I take 1/2 times the base, the height, which is 3, times the sum of the bases, which is 2 plus 5. I have 1/2 of 3 times 7, which is 21 over 2. And then we have a square root of 4 minus x squared from negative 2 to 2. There are my bounds. If x is negative 2, I have 0. If x is negative 1, I have the square root of 3. If x is 0, I have 2. All right, this is a half a circle. And if I'm looking for this area, I have 1/2 pi times r squared. R is 2. 1/2 pi times 2 squared makes 2 pi. There are two special definite integrals. If f is defined at x equals a, then the definite integral from a to a is f of x dx is 0. There's no area between no space. And if it's integrable on a to b, then the definite integral from b to a is equal to negative definite integral from a to b. So basically, if I have the definite integral from pi to pi of sine of x dx, the area there, the answer is 0. If I have the definite integral from 3 to 0 of x plus 2 dx, I have negative definite integral from 0 to 3 of x plus 2 dx. In the last problem, we just saw that this area right here is 21 over 2. So I just stick a negative on it. The additive interval property. This one basically says that you can take a definite integral and you can break it apart. From a to b, we can go from a to c plus c to b, as long as c is in there somewhere. So I would use that for this problem. The absolute value of x. The function looks like that. So I would take my definite integral from -1 to 0, and then 1 to 0. It's actually negative x dx plus the antiderivative, the definite integral from 0 to 1 of x dx, because we can break that function apart those two ways. We have 1/2 times base times height, which is a half, plus a half, which gives me an area of 1.